Most people picture AI interactions as a straight line. You type a prompt, the model reads it, and it outputs a text response. But building autonomous agents shatters that mental model. An agent operates inside a continuous, spinning execution loop that swallows that static line entirely. An agent run is an ongoing cycle of deciding, acting, and reacting, rather than a single transactional prompt. Inside this cycle, the large language model acts strictly as a non-deterministic reasoning engine. It is simply the brain, interpreting data and making choices. Deploying a probabilistic brain directly into a live environment is a recipe for chaos. It requires a deterministic wrapper to keep actions predictable and safe. We call this wrapper the harness. It is the surrounding infrastructure, made up of memory systems, equipped with predefined tools and strict guardrails. Transitioning from writing clever prompts to engineering production-grade agents requires shifting your entire focus to this harness. It is the infrastructure required to constrain, steer, and empower the model. Out of the box, large language models are completely stateless. They have no memory of what happened 5 minutes ago, let alone yesterday. To create any sense of continuity or agency, developers have to manually inject state into the system using external memory structures. This memory injection architecture relies on 3 data pipelines feeding the LLM's context window. First, procedural memory in a database stores rigid skills. Second, semantic memory in a vector database stores fuzzy facts. Third, episodic memory uses a summarizer agent to compress past conversations. But injecting state creates a bottleneck. Dumping all 3 of these databases into the LLM at once overloads the context window, driving up costs and degrading the model's reasoning capabilities. The agent has to retrieve only what it needs. Semantic search excels at finding fuzzy, unstructured text based on meaning, while structured SQL queries are required for executing exact constraints, like filtering by specific dates. This workflow illustrates the optimized solution, hybrid RAG. You use a strict SQL filter to narrow a massive dataset down to the correct date range, and then apply a semantic vector search to rank the remaining documents by conceptual relevance. Without these external architectures, every single run starts with a blank slate. Structured memory gives the agent the context it needs to adhere strictly to your business logic and user preferences. Once the agent has the necessary context, it now has to take action out in the external environment. There is a widespread misconception about how this works. LLMs do not execute code. They cannot run APIs, click virtual buttons, or send emails directly. Instead, the model emits a perfectly formatted JSON payload representing a tool call. The harness intercepts this JSON, executes the external API on the model's behalf, and routes the resulting raw observation straight back into the LLM's context window. This continuous routing forms the core decision cycle. The model decides on an action, emits the JSON, observes the result provided by the harness, and decides on its next step. Treating the LLM strictly as a text-to-JSON routing engine completely decouples its reasoning from system execution. It creates a highly secure, modular architecture where the vulnerable model is isolated from direct access to your infrastructure. Running a continuous decision cycle introduces a severe operational risk. A probabilistic engine can make compounding errors, resulting in an infinite loop of failed tool calls and retries. If you try to build an agent by merely chaining prompts together, the system will inevitably collapse in production when it encounters one of these unconstrained loops. The solution is loop engineering, the architectural practice of designing exactly when and how the execution cycle must terminate. The first and most vital loop constraint is a hard stop limit. Hard-coding a maximum number of iterations ensures the process dies after a set number of steps. This is your ultimate failsafe against a runaway loop draining your compute budget. You also need dynamic stopping conditions, like a convergence check. The system constantly calculates the delta between the LLM's outputs across iterations. When the output stops changing meaningfully, the harness recognizes the agent has reached a conclusion and halts the loop. Before that final payload ever reaches the end user, it must pass through one last safeguard, the validation gate. A validation gate uses a secondary, deterministic rule engine, or a very strict checker LLM, to verify that the final output format matches your exact requirements. For high-stakes actions, you can configure the gate to enforce a human-in-the-loop pause. This physically breaks the autonomous loop, holding the action until a human provides manual approval. These specific loop guardrails are what differentiate a fragile local demo from a highly reliable, production-grade software system. We now have a fully assembled Agentic harness, a probabilistic reasoning engine supported by injected memory pipelines, executing actions through middleware, and constrained by strict loop engineering. Taking this complex structure from a local environment to a live deployment introduces a new operational reality. This node link mapping shows an execution trace graph. Because the core engine is probabilistic, things will go wrong in unpredictable ways. Debugging an agent without deep system observability is exactly like trying to debug a black box. You have to use execution tracing tools, like LangFuse or Langsmith. These map the entire graph, recording exactly what the LLM saw in its context window, the exact JSON it emitted, and the latency at every single node. Tracing lets you isolate diagnostic failures. You can instantly distinguish between an agent hallucinating because of bad retrieval versus failing because of bad reasoning from a prompting issue. Managing this requires LLM Ops and a dedicated evaluation framework, or eval, to measure these specific failure modes at scale. Since correctness in language models is often fuzzy, the standard practice is the LLM as a judge paradigm. You deploy a secondary model with a strict rubric to score outputs for factual accuracy and tool use correctness, scaling your testing without manual human labeling. This chart depicts the mandatory deployment pipeline for non-deterministic software. You reproduce the trace, fix the harness, run the eval suite, and approach the merge gate. The unbreakable rule of the merge gate is simple: never ship code based on a feeling. You only deploy to production if your automated eval scores improve or stay completely flat. Achieving true AI autonomy is not about waiting for a smarter model to be released. It requires building a rigorous, observable harness that makes a non-deterministic engine safe, useful, and ready for continuous iteration.